So yeah, workshop 3 will basically be about this thing called gradient descent, which is sort of what I just told you about, this method of figuring out how we're going to move around our weights and biases in response to some sort of error. And so I guess just to kind of recap for the folks who weren't around previously, we can take a peek at how like different weights and biases change our problem. So like, let's say we had this set of data. And we were basically trying to determine a linear regression to determine like, for given a linear regression with some param that's defined by some y equals wx plus b, how do we find a w and b that fits this set of points well? And we talked about error as this thing called mean squared error, where we basically take the predictions we get for a given w and a given b, and we check how close or far they are from our actual values. So let's say, for instance, we pick some w, we'll test some, and that might be a bit too thin. We'll test some w equals 2 and b equals 3. And maybe that'll give you a linear regression that looks like this. And basically, to determine the error, we'll just sort of compute the distance from our actual points to some predictions given the same input and see how far away they are and then square them, mean squared error. And let's say for this instance, we see that the error is high. Well, we want to make the error as small as possible, and that'll basically give us a regression that best fits the data, right? So we want to adjust accordingly. So let's say we get some response from our graph that with this regression with these parameters, w equals 2, b equals 3, our error is high. Which direction do we now need to move w and b so that we can reduce error? That's sort of the crux of the problem. So let's say, for instance, we see error is high. We try another set. We say w equals 1.6 and b equals 2. And we say, okay, so this line might look something like this. And now we do the same thing. We compute the mean squared error as we did last time. I'm going to define that right here for y'all. That's just so we can kind of review it. So the mean squared error basically is going to be the summation of your points, all your input data, the predicted value y hat minus the actual value y squared. So we're going to use the error metric and we're say this time we did better than last time. We got a lower error because, as you can see, the regression with this set of parameters fits the data better. Now we're going to say, okay, well, it's not really perfect yet, but we know we've gotten better. So we don't need to adjust our parameters as much to fit this model better. So by basically iterating over some weights and biases, and after each iteration, checking how the error looks and seeing how the error looks relative to the previous trial, our model can sort of build some intuition and figure out how it wants to move the weights and biases around to minimize the error when fitting a line onto the set of points. This is for the linear regression case. And in essence, what we can think of, what we can think of this problem as is an optimization problem, where given some set of data points and some way to fit these data points, how can we optimize it so error basically is minimal? And okay, we'll try to get this thing to cooperate. Hello? Can you work, please? Okay. Again. Okay, there we go. Alrighty. So let's start looking at this. So the first part of this notebook kind of covers a visual way of exploring gradient descent. So I talked about earlier, sort of mathematically finding a fit for a set of points that like basically fits the best and has the lowest MSE, the lowest mean squared error. Well, sort of physically what's going on is you can imagine this. Like imagine you're standing on a collection of hills and your desire is to find the lowest point within this set of hills. And there's a bunch of hills, right? So there's going to be valleys, various valleys, some that are going to be deeper than others. And our goal is to basically find the lowest point in the set of hills. And how can we figure that out? Well, we can basically just walk around on these hills, right? And we know that if we're walking down, then hypothetically, we should be going towards a lower point. And we're going to keep walking, and we're going to notice that as we approach basically a lowest point, the hill should be getting less steep, right? Because it's kind of approaching flat ground. It's basically approaching a point of inflection, like the bowl of a parabola, you might notice. But in this instance, we're going to be walking in a 3D space, right? We're walking across hills. It's not as simple as kind of finding the bowl of like the lowest point, the trough of a 2D parabola. And the thing is, this optimization problem isn't that simple because there's various sort of factors that are going to influence how things go, and there's going to be some traps that we're going to run into. But the basic intuition, I think the basic picture you can keep in your head is basically you have this, you're looking for a minima. You're basically walking around the set of hills looking for the lowest point, looking for the deepest valley, basically. In this instance, the hills basically represent this thing called loss, which is basically like your error. It's the thing you want to minimize. And so by walking down them, you can sort of reduce your loss gradually. Now, the different places you walk to in this instance basically can represent different parameters. So let's say I walk to like one point on the hill, the steepness of the hill and the distance I have to like the lowest point is going to change, and I'm going to feel different. I have some different W and some different B now. I've tried to fit a different model, basically. So those are basically the values in sort of our physical picture. So just some terminology. So we use weights and biases as our variables, W and B. And a term for loss is J. This is just sort of a convention. You'll also see E sometimes, like error. And an additional parameter that we're going to talk about is this thing called learning rate. Basically, how big of a step are you going to take down the hill before you check how steep the hill is and how close you are? Not how, I guess just how steep the hill is. So for instance, you could designate a big learning rate and you would just walk a long time or walk very far down before checking what your error is looking like. You could set a small learning rate, walk a little bit, check again, walk a little bit, check again. That's basically what learning rate is determining in this instance. And learning rate oftentimes is notated with the Greek symbol eta, which is kind of just the n with like the other end of the n is sort of long. Kind of looks like this. But yeah, that's just some basic terminology. So let me make this thing go somewhere else as well. Oh, well. But yeah, and the loss, why this thing that's called gradient descent is because this thing called the gradient is basically is the hill that we're going down on. The gradient is basically a slope, but since we're looking at a 3D picture, we're looking at sort of vectors. There's going to be some sort of direction associated with the slope, right? Because when we're walking down a hill, we can't just walk straight down. We can walk down into the leftish, down into the rightish. So this is why we call this a gradient. It's just basically a mathematical term that describes a slope within like a vector field, basically something that has a direction associated with it. And gradient descent, well, we're basically descending down the gradient until we can find the optimal point where the gradient is minimized. And what does minimizing the gradient mean? Well, basically that means we've kind of reached a goal, right? Because if we're at a lowest point and it's kind of turning into like a point of inflection, it's a valley, then your slope there is going to be 0, right? So that's why we're kind of trying to descend down to a minimum. Before we get into the more like 3D gradient descent case, we're going to look at some simplified 2D cases. But before we even do that, anybody have any questions so far? Yeah. We're not necessarily looking for the highest rate of descent because error landscapes can oftentimes be pretty weird. I'll show some pictures later. We're basically looking just to minimize the gradient. I mean, going like down a steep part is good because we know we're going quickly down, like we're reducing error pretty quickly. But that isn't necessarily like always a concrete metric that like sort of algorithmically we're searching for. But yeah, it's a good indicator. So
If you have like a bunch of hooks, like how would you like, I understand how you'd find the minimum like one value. How would you know to swap to like a different value?
Yeah, it's a big problem we're going to talk about later as well. That's a big issue with gradient descent sometimes. But yeah, let's first talk about this more simplified 2D case. So like we said earlier, we looked at this thing called mean squared error, and it's just a way that we define error. And we also will kind of look back to that earlier regression case where we have y equals wx plus b, just because it's a fairly simple way to look at these as like an example problem. And let's just first take a dummy case, right? We'll just imagine that our error landscape, the hill that we're walking on, we know in advance. We'll just say that it's a parabolic function that's defined by, that's error as a function of y equals y tilde squared. Now, typically when we're doing this optimization problem, we have no idea what the error landscape actually looks like. We are basically like testing the error as we permute our parameters and kind of building out this picture over time. We don't actually know this, but we're just gonna pretend we know it in this example so that we can analyze some things. And yeah, this is also a pretty unrealistic example just because typically when we have a problem we actually want to apply machine learning to, a simple parabolic function probably won't quantify the error. But if we just look at this, y equals, we'll imagine j equals y squared, even though this is something different. But if we look at this parabola, what sort of mathematical formalism can quantify how steep it is? Anybody got an answer? Yeah, what's up? Exactly, yeah, the derivative. The derivative at some point will basically give us a way to quantify the slope, the steepness of the parabola. And like we talked about last time, this is why mean squared error with that squared term is important, because much of our architecture for finding these errors is going to be built around the derivative. So we need to have some sort of error with a squared term, so that with some sort of exponential term or something like that, so that when we take the derivative, it's actually a meaningful quantity and not like just some constant or goes to zero.
Usually estimated computational derivative.
Pardon?
Would be computational estimated derivative the real case?
Yeah, we would just be computing the derivative like at the different points as you perform this algorithm over time. But yeah, so let's just look at this example. So we're going to take the derivative of this error function, and we're going to get 2y as our answer. That's just going to be the function describing the slope over the parabola at any given point. And when we look at this, we're looking for the point of minimum error, right? So if we know the derivative is defined by 2y, solving for that, we basically know that the point of minimum error is going to be 0, 0. And we'll look at how we arrive there computationally. So let's say we have this parabola, and as we mathematically solved earlier, the point 0, 0 is the minimum. How do we know that? Well, we have this y, j equals y squared. So dj, dj dy is equal to 2y. And if we want to minimize error, we're going to say 2y equals 0. So that means y also equals 0. So the point of minimum error is going to be at 0, 0. Does that math all make sense? But so we were able to discern that because we cheated, right? We predefined an error landscape that we knew so that we could use it for the sake of a toy model. But how are we going to arrive there with gradient descent and iteratively over calculation? So let's say we begin our estimation of this parabola. And we start at this point on the error landscape. And we say, okay, well, how is this? We're going to look at the error. We're going to compute a derivative. We're going to say, well, that kind of sucks. The next thing we're going to do And right now our model only has 1 point, so it can't really make any connections or infer anything. So maybe it does something stupid and it says, okay, let me go even further away. I'm gonna measure it again. And suddenly the error is even worse, right? As we're at a steeper part scale. Wow, this sucks even more. So that kind of informs me that I'm going in the wrong direction. Maybe I'm gonna go in this direction now. Let me change colors so this doesn't get too complicated. So I'm gonna go down this time. And I'm gonna measure my derivative again. And then all of a sudden I see, well, they got better. So I'm happy. Well, if I am going in this direction, I'm getting happier. Why don't I continue going in this direction? I'm going to measure again. And then I see, oh, it got even better. So that further solidifies my belief that I'm going in the right direction. I'm going to keep going, keep going, keep going. And then maybe I don't know that I'm necessarily at the lowest point. I go one more. And suddenly my error goes like this. And I say, oh, I got worse. So then I go back. And then I eventually oscillate to the local minimum. That's how computational we're going to be doing this. If we don't know what the actual error landscape looks like, we're going to basically iteratively fit some parameters on our model. We're going to compute the error, and then we're going to keep doing that for different permutations of parameters until we gradually get a sense of the direction we need to go to arrive at the local minimum. Does that high-level picture make sense, everybody? Yeah, what's up?
Theoretical situation where you already at the peak, let's say, right?
Mhm.
The descent on one side is steeper than the descent on the other side. Would you try both sides before deciding which way you go?
So like something, let's say you had like something that looked like this, and you were like here, for instance.
Yeah.
Yeah, so that's one of the problems we're gonna talk about later. So actually, let me make this even like a bigger issue. Yeah, exactly. So yeah, you might like go this way and then you'll get stuck here eventually, but then this is the actual absolute minimum, right? So that's one problem you can run into. But the thing is, the good thing is we can kind of like iterate over these things and we can inject maybe some randomness into it. So maybe this time it went that way, right? But the next time it might go this way and it finds this. And since we've done this over multiple trials, we can then compare and say, oh, well, this one gave us a better result than this one. So then I know this one should be the way to go. But yeah, it's definitely a problem that we can fall into the trap into. Like if we have a landscape like this, it might just fall into the wrong spot. Yeah, that's a good question. And okay. So yeah. And we basically were able to kind of iteratively build up this error landscape and figure out where the local minima is. And yeah, this is basically an outline of how we're going to be doing that. And what this looks like mathematically, if we were to kind of describe it with one equation, is this thing. Delta W equals the partial derivative of partial J, partial W. So what does this mean? Let's talk about it. So in English, updating our weights results in some change in error that directly arises from the modification of our weights. So delta W is equal to partial J, partial W. So this basically is telling us that the change in our weights arises from the change in error relative to some change in the weights. So shifting our weights results in a shift in error. That basically encompasses how error responds to us tuning our parameters. And that's sort of just the kind of mathematical equation. Not a huge thing that you really need to know, but I think it's nice to kind of have these in parallel with our more physical images. And yeah, as we sort of talked about already, there are some concerning problems where you can sort of get stuck in these local minima that are not absolute minimum. So as we were talking about earlier here, you can kind of oscillate to the wrong spot and your model will just think that this is the best and completely neglect this. But fortunately, we do have some strategies to help with that. Two examples that we're going to talk about here are stochastic gradient descent and momentum, but those will kind of pop up later. First, I kind of want to address this learning rate question. So earlier we talked about the learning rate in the hills, where kind of like the learning rate determined how long I would kind of go down for until I rechecked my error. And learning rate, basically, when we train a machine learning model, is an important parameter we want to consider because it can lead to problems, but it can also lead to ways that your model can be better, for instance. So we're going to look at a couple of cases. The learning rate is too small, it's just right, and too high. So what happens when the learning rate is too small? Well, let's imagine a hill analogy again. Let's say every time we take a step, we recheck our error because we're just really anxious and we really want to know how well we're doing. Well, what's the problem with that? Why shouldn't we just check what's going on, like every single tiny movement? Yeah, go for it. Exactly, it's going to take forever. Machine learning models, at the end of the day, are these really big things that are built on repetitive linear algebra computation. So if we check these things too quickly and too often, our model is going to take forever to train, and it's not going to be able to converge to a local minima in a good amount of time. That's sort of this first figure. What if we kind of don't check often enough? What if we, like, the learning rate is too high, we don't check often enough at all? What happens then? Any thoughts? Yeah, I'll give it again.
The chance that you're gonna hit the minimum if you're like jumping too far is very, very low.
Yeah, exactly. If we basically check, we don't check frequently enough, we don't know basically like how far we've traveled or where we are. And that kind of just messes up how we're going to figure out where the local minima is. To give that sort of iterative example, let's kind of look at a diagram again. Let's say we're on this curve and we start here, right? And we have a really big learning rate, so we check super infrequently. So let's say we kind of walk down here. We started initially with a pretty high slope. We walk down a little bit and we say, okay, how are we doing now? Now we come to here and we say, oh, we got a lot better. So that means I'm going to keep walking. I walk, 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 walk. I walk over here now. And then we check our slope again and we're like, oh, wait, this got like really bad again. So that means we're going in the wrong direction. So then I start walking in this direction again. But since I check so like infrequently, I might just walk back over here. And suddenly, like my error is really bad again. And this informs me I need to walk to the other side again. But since we check so infrequently, we move around too much before we resample. And so we're kind of just stuck in this loop of hell where we go back and forth and back and forth. And we never actually find the local minimum because we don't sample enough. Yeah, question?
You store more than just the previous value. For example, if you're to start like here, you swing over here, and then you go back to here, you forget this initial.
No, you actually don't forget because kind of like all these errors are basically chained together, right? So you'll always sort of retain a little bit of info about that.
Like it's sort of like this is worse, but this was better than that, so I should go in that direction.
Yeah, perhaps. But some like this is very dependent. Like oftentimes you'll just find really oscillatory behavior that'll just kind of wind back and forth and back and forth. And you can't really get out just because you're checking way too infrequently. And just at the end of the day, these are actually fairly simple, like mathematical models. So they don't really have like too much of an architecture to deal with kind of weirdness and hopping around. And yeah, so if your learning rate is just right and you check like in the perfect balance of in-betweens, then you'll kind of just be able to walk to the right place in not too long of a time and without sort of jumping around too much. And what does learning rate look like mathematically? Well, basically, it's the scaling factor that ends up in front here. And what that's doing is basically telling us how much we modify our weights, right? This delta W, based off the error. So if learning rate is really, really small, then we don't modify our weights very much, so we'd never walk around all that much before we recheck. But if it's really big, then we always walk around a ton before we check again. And that's like why this simple little scaling factor in front of this partial J partial W really changes how we kind of navigate to the local minima in our error landscape. Does all this make sense so far? Any questions? Okay.
Would it make more sense, let's say, for the dynamic efficient to change the smaller slope? The less steep slope would be a smaller step.
Yep. Exactly. Yeah, so you could also have like basically a dynamic learning rate, right? There's actually things like that where they have some sort of adaptive learning rate that'll like move around based off like things like iteration number or based off like how steep something is. But that can also be problematic. Does anybody have any thoughts on why that might be bad? Yeah.
So if you have a learning rate, like let's say you're going down to the slope and then you take a smaller step every time you get closer, it's possible you may never reach the point because you're taking smaller steps. It'll just take you forever to get that. Right?
Yeah.
I think what you need to do is then take an overstep and then find where it's like between two things. Like ideally, I think that's what you want to do, right?
Yeah, I mean, I think I'm not super sure about like the second method, but at least I think you're completely right in the fact that you may also just kind of get stuck and never converge, right? Because like if you're taking smaller steps as slope gets smaller, what if you have an air landscape that looks like this, right?
Oh,
Then you would never find this point, right? Because your learning rate gets too tiny here. Yeah, and then you're kind of stuck. So that's one problem. Anybody have any other thoughts on why kind of having these adaptive learning rate schemes might be tough sometimes? Let's see. But yeah, I mean, the biggest sort of one is the fact that like sometimes you may think you're converging, but you never really ultimately know if you've converged or not. And what like that just this is a really big pitfall. However, I would just say that like definitely adaptive learning rates can be very helpful sometimes. So I wouldn't just kind of push them aside. The neat thing, right, is that these are all computational things. So we can feel free to iterate over like a huge amount of permutations of how we choose to do things. And then we can just benchmark them and see how they do against one another, right? And in essence, oftentimes that's basically how you make your machine learning model better. You do this thing that we'll talk about later called hyperparameter search, where you just iterate over a bunch of garbage and you generate graphs of how loss and whatnot is changing. And then you just say, okay, this one looks the best, so I'm going to pick this random permutation of parameters. Any questions so far? Okay, so let's kind of level up then and talk about the 3D case. So, I mean, the stuff is basically the same, right? But we have a slight change in mathematical framework. And that change is basically we go to this thing called the gradient, which is this upside down triangle thing. And what does that mean? I think light mode would be good for this graph. All right, so the gradient basically, as we talked about earlier, defines how we find slope, quote unquote, in a vector field, in a field with in a landscape where there's also direction associated with it. And this sort of thing is what we're going to be kind of parsing through when we actually compute our error landscape. So the gradient basically defines that, like, if I'm on this point, right, I'm actually not just having some slope of some magnitude, I'm also headed in like this direction going down. Or like if I'm on this point, I have some slope, but also I'm going this way. So the gradient basically just builds in this directional thing. So it kind of like vectorizes our slope so that we can basically describe what's going on in 3D cases. And like all the error estimation, all the error optimization in most of our cases is going to be for 3D landscapes. So that's why we use the gradient. Now, why might finding the optimal point now be tougher now that we have a 3D case? Any thoughts?
Directions.
Right, there's a lot of directions to take, right? We've just increased complexity. It's not simply just a matter of absolute magnitude of slope. Maybe you might be moving like this way or this way or this way or this way. You know, it's much tougher to find where you're going to go. Any other thoughts? Yeah, what's up?
Like if you have like different holes, and like your direction will like lead you towards a certain hole. You don't know if that hole's deeper than the other hole you're going to.
Yeah, exactly. There's sort of more routes to fall into local minimum. Yeah. And one other thing that, like, this probably isn't everything, but just an additional point that is gonna kind of look really gnarly is by moving to 3D landscapes, we have the opportunity for much more disgusting error landscapes. So I'm gonna give you a preview of some of the later stuff, but if you look at something like this, right? Like, where the hell even is the minimum? Like, you could be walking along here and suddenly fall off here, or fall off here, or fall off here. So by increasing our dimensionality, we basically open ourselves up to much more complex cases, right? Complexity is just scaled upwards. We're going to look at those some more later.
What if the 3D landscape, what are the variables?
Oh, so the 3D landscape here doesn't actually have any association with like W or any of that stuff. That's all sort of baked into the error itself. Like in the case of like it might just be in like XYZ, right? But our equations are now gonna also be functions of all three parts, right? So it might just look like y equals W x y z plus b.
Oh,
Yeah, yeah. So we're not actually sort of baking all the axes and all the dimensionality into like the different like parameters and stuff, but like our error just kind of looks different now. Like when we get this J out, it's not going to be like a 2D thing anymore. It's just going to be X, Y, Z, basically. Yeah. And that's why we have like the gradient, right? That sort of throws us out. Since it's like a vector operator, right? It's going to throw us out vector values.
I'm assuming like more complex machine learning algorithms go more than 3D, right?
Probably, yeah. I actually haven't looked too much into it, but yeah, I would assume you could.
Just the dimensional number of dimensional margins and stuff. Hundreds of them.
Yeah, exactly. Yeah, as you increase your features, it's gonna make your gradient descent tougher. Yeah, that's why typically initially we talked about when we get in data, we don't want to like we want to engineer our data, right? We don't want to just basically have a data set. If it gives us all these values, we're just going to throw all of them in our model. We're going to try and delete useless features.
Oh, because more features can get a more precise graph, but making that graph more precise. Right?
Oh, just more features kind of just adds more noise. Like if we have a lot of features, the individual features aren't so clear anymore, right? And there's just a lot more kind of like voices in the crowd that are going to muddle how things change, basically. But yeah, I mean, similar to the 2D case, as we talked about, you can encounter misleading local minima. You can fall into this hole, this hole, this hole. There's just a bunch of things you can fall into. And this makes life pretty hard for us. And we have to come up with methods to basically try and escape this. And we're going to talk about just two sample ones. There's actually quite a bit more out there, but these are just the two I've picked. Some ways in which we can kind of escape these misleading local minimum. The first one is this thing called stochastic gradient descent. And what is exactly a stochastic process? Well, it's a random process. So we can kind of think of this as random gradient descent. Let's just look at some plots of stochastic motion real quick. You can kind of see that we basically have this graph that's being generated from this thing called Brownian motion, which is basically a random walk of, for instance, like a particle or something. What does that exactly mean? Well, imagine we have like a particle, and let's just look at these in some weird units. I'm just going to call them like tie units or something. And in tie units, you can either walk up or down one, and the particle just has a 50-50 chance of taking either path. At the next point, it has another 50-50 chance. And we're just going to propagate this outward. The particle is basically taking a random walk. That's an example of a stochastic process. And we're going to try and borrow that stochasticness and inject it into our gradient descent so that our model has a good chance of not messing up. And does anybody have any just like kind of ideas about how injecting a little bit of randomness into our model can help it not get stuck in these local minimum? And I'll give you a hint on what the randomness is going to look like. It's going to be, instead of sampling the entire set of data points, you know how earlier we talked about when we were doing mean squared error, we basically took all of our predictions and then calculated the error with all of our data points. With this stochastic method, we're basically going to choose a random set to compute error from. So how might that kind of change things and help us get unstuck in the local minimum? Any thoughts? If we're like kind of approaching this fake bowl, how might some randomness allow us to not get stuck in here and kind of get out of there. Go for it.
I presume randomness can like generate sort of random values, some of which could be big enough for us to jump over the ridge and then go down. But at the same time, I feel like this could work the opposite way too, where on the other side, on the right side of the ridge, it could make us jump back.
Mm-hmm.
So I'm not really sure if that's like helpful, when it actually works like both ways.
Yeah, so I mean, what you said is exactly right. Like, let's say we're here, right? And but we actually ultimately want to get down here. I'm going to draw this in a better spot. So we have like this. Let's say we're here and we want to jump down here. Without some randomness, we might just say, okay, derivative is 0. We're happy, we're at a minimum, and it's going to settle here. Well, maybe with a little bit of randomness, it'll suddenly just decide to say, oh, I'm going to jump out here, and it's going to recheck and be like, oh, what the heck? Like, there's all this other stuff here, so I'm going to keep going down. And yeah, like you said, there's the other problem where the function might basically be here and then it like walks back up and out. Yeah, but the thing is, typically when we're at like an absolute minima, what we're going to see is that we have basically some information that kind of tells us that this minima is sort of like better than perhaps local minima that we were at earlier. And that's going to sort of help inform us. So let's say we had like something like this, we had like an absolute minimum, or even something like this. Like, we know that by the time we're here, we perhaps traversed something like this, right? Or we came in from the other side, and we know that by coming down from this side, we walked down a lot and it was super steep. So the model has some information basically that's gonna diminish the magnitude of the randomness basically. So it's gonna be more likely to walk out of minima that are less less convincing, and it's more inclined to stay in minima that are more convincing, because that like the magnitude of the randomness isn't going to be that huge. So that's why like oftentimes SGD, stochastic gradient descent, will sort of like, it might help you walk out of a shoddy local minima, but typically it'll stay in a good absolute minimum. But yeah, so in typical gradient descent, we're kind of computing derivatives for every prediction. And aside from just the randomness we talked about, why might this also be like not a great choice? Especially for models and data sets with like a lot of data. What's a bad point about this? Any thoughts? How might this be not so great for us as we scale our models up and increase the amount of data? Anybody else? All right, go for it.
So if you're looking at like a large data set with like a lot of different, if you use the entire data set all the time, like you're going to be looking at something more of an average, and you're probably going to be missing the holes that are like in specific locations. Whereas if you like stick to like random sets, if you think of it as like focusing as like on particular locations, which could get you towards those small holes as opposed to looking at the entire thing.
That's a good line of thinking, but that's not exactly right. So in the case where like you have a lot of data points that you're looking at, you kind of get a pretty informative picture, although it kind of can lead you to like kind of majority votes getting stuck in certain local minima. But the problem with actually computing the derivative for every single data point is that like this just is really computationally expensive, right? When we do this, it's actually really simple. Yeah, I like the idea, but yeah, it's computationally expensive. If we're gonna compute 10,000 like derivatives for every single error step, we're kind of just shooting ourselves in the foot. So yeah, those are two kind of things that SGD helps out with. It helps us kind of get unstuck from local minima, and it also allows us to save a little bit of computation time, because what SGD basically is doing is, instead of looking at error from all of the data points, so initially, let's say we had a data set with n samples, right? What gradient descent is doing is basically looking at the error over the sum of all n samples. Wait, that's not how you write summations. It's like this. Y I hat minus y. Yeah. So we're basically computing the distance, the mean squared error for every single point within our data set. With stochastic gradient descent, basically the bare bones version of it, we're just gonna do this. We're just gonna look at a single point, a single random point out of the data set. And this actually injects a ton of randomness, right? Because let's say we had this graph again, right? And we had this set of linear points for regression. And our initial plot looks like this. If we choose to sample, like what point we choose to sample for error really changes things, right? Because if I sample this point in my SGD randomly, suddenly my error looks a lot bigger. But if I sample this point, suddenly it looks really good. And so it's that process of randomness of how our error actually looks in the iteration that helps us kind of have a little bit of stochasticness and randomness in where we're going to move around. Now, sampling one point isn't necessarily a good idea, right? Because of just how much a single random event can swing our overall error. So oftentimes when we actually implement SGD, we do this thing called mini batch SGD, where we maybe say, we're going to designate a batch size of how many points we're going to sample look at error. So for instance, we could do mini batch SGD with 4 data points. So instead of just looking at a single one, we're going to say, oh, we're going to take 4 of them and then look how that the MSE looks. And this is basically going to help us avoid skew from a single point, but it's still going to keep that little bit of randomness. And you could actually test this out yourself once we kind of build up there. But as you increase the batch size of SGD, what happens? Let's say, let me write this out. For mini batch SGD, as batch size B converges to N, the total number of data points, what happens? That's true, but like, I guess more what happens in terms of what the process looks like. What does it sort of become as our mini batches go to N? Yeah, go for it.
It becomes more like if you would have just done a basic like approximation test.
Not exactly, because like in this case, we're looking at errors. Yeah, that's it.
Just become just like doing gradient descent.
Exactly, yeah, it just becomes gradient descent, right? Because eventually, as our batch size approaches N, we're just going to end up looking at all of the data points, right? So yeah, for mini batch gradient descent, as batch size B goes to N, mini batch SGD just goes to regular gradient descent. And that's sort of just the way you can kind of link these two things together. Yeah. So a sort of visual comparison is of how gradient descent might look. Let's imagine we're taking a bird's eye view from one of the troughs, one of the valleys, and this eyeball looking thing in the center is our point of minimal error. Regular gradient descent, where we sample every data point, it'll follow a fairly straight curve because we basically, by filtering over so many, by looking over so many data points in each iteration, we smooth out a lot of the skewness and the stepping that might occur if we do stochastic gradient descent and only look at small batches of data. Now, if we kind of think about this from the bird's eye POV, how might this kind of jagged movement help us kind of avoid or discover different local minimum and get out sort of the predictability of gradient descent. Yeah, go for it.
Well, if there was a minimum on the way, because it just goes back and forth a little bit, they discover it.
Exactly, yeah. So let's actually draw our own little curve, but let's make it a bit more messed up. So let's say we have these things and we're kind of trying to converge here. But let's say there was another one like right here and like another one, an even deeper one. I don't know how to make these look deeper, but we'll just have to bear with me. And we'll kind of, let's label these with text because I don't know how to draw 3D topographical things. Deepest, deeper, wait, no, that's not how that works. Medium deep. And not so deep. And let's say we started here. If we were doing regular gradient descent, we sample over every data point. And we might just end up walking here every single time, right? But let's say we added a stochastic process into it. Maybe we walk like this, and then we kind of fall into this one, right? Maybe we walk like this, and we sort of sit on that edge and we never figure out where we're going. And then we suddenly fall in here and we're like, oh, and then we fall into this one. And then we can kind of also walk down here again. Since we are doing an iterative process, what stochastic gradient descent gives us is it gives us an opportunity to basically try different routes to walk, right? And by walking in these weird ways, in these random ways, we might accidentally discover different features of our error landscape that will help us out. So yeah, that's sort of stochastic gradient descent. Any questions on that? Yeah.
Right? You would just retry again and see if you can find a deeper hole, then that's like the iterative process, right? So you kind of just run the process multiple times.
Yeah, that's definitely. So it's not necessarily like a voting mechanism like that, but that's definitely a way that SGD can help us. It can like take us down a different path some other time. That'll give us better parameters. Since like eventually when we do start training neural networks, we'll do this thing called epochs, which basically are like repeated trials in which we're trying to refine our parameters. But that was like sort of the first case, but there's also the second case of, oh geez, this is going to be a tough drawing, but let's say we're in this hole, but there's these two minima that we can get sucked into. And if we're walking like with SGD, or if we're walking with gradient descent, just regular gradient descent, what might happen is the way our data is formatted will make us walk into here every time. But with SGD, or like once we walk in here, we can't get out anymore because that just is the lowest error. But with SGD, we might be walking, we're walking, and we're here, right? But there's a little bit of randomness, so we might just walk like this a little bit. And suddenly we'll find this part and we'll fall into this part instead and help us discover that the accidental error. And before I continue onwards, I have a question to pose. Let's say we had this landscape, right? I mean, from this graph, it looks like there's a finite amount of points within this chart. Why don't we just compute the error at every single point in this chart and just find the lowest one? Why don't we just do that? What's the problem? Any new customers want to give a try? This is an idea we kind of touched on earlier. And this is like a really simple thing, so don't overthink it. Why can't we just compute the error landscape? Yeah, go for it. Yeah, there's too many points, right? It's super computationally expensive, once again. Like, we look at this on a grid and we're like, okay, maybe there's a finite amount of points, but like, to construct something like this, even if you interpolated between points, these landscapes are really big, so it's just going to take us forever, you know. And oftentimes we just don't really have the power or the time to be able to do something like that. And as your tasks kind of get more complicated and scale up, these are just going to look even more disgusting. So the problems you care about the most, the really complex tasks, are going to have some of the most disgusting error landscapes. So we talked about one thing, stochastic gradient descent. Let's talk about another thing. I'm going to omit those for a second. This thing called momentum. So let's just think about momentum as a physical thing for a second. So momentum is this optimization method that's going to help us get out of fake local minimum. And in terms of physics, what exactly is momentum? Well, if we have an object sort of moving and it has some momentum, what is it going to do? It's just going to keep moving, right? It's not going to suddenly kind of double back and go in a different direction if it's already going in a certain direction. So like, let's just think about this physical principle. If we have an object that has been moving along in this certain direction, certain path for a while, and it doesn't really want to change direction, how might this help us with escaping local minima? Thoughts? Go to somebody else. Thoughts? Let's say we were on this curve. How might some momentum help us out? If let's say let's just think of this not as a curve. Let's just think of this as a slide. You're like a 3-year-old going down a slide. If you're just heading down this direction and you're pretty fast, and you hit this hump all of a sudden, if you're going down that direction, what's going to happen? And you have momentum, right? Yeah, the hand motions are sufficient. You're just going to go, whoop, and you're just going to keep going, right? So that's essentially what's happening with momentum in neural networks, right? If you have an error landscape and you are going down and you're kind of acquainted with going down this direction, well, just keep going, right? You have some built up momentum that's going to take you past their region. And let's look at this in terms of some math. Earlier, we talked about this equation. Just pretend that this E here is a J, but so this change in weights is equal to how the error is changing relative to the weights scaled by a learning rate. Well, this time with this thing called momentum, we're going to be considering how much the weights changed in the previous iteration. And there's also going to be a scaling factor, but that's going to get tacked on to how our weights change this time, right? And what this is basically telling us is how fast we were going, right? What our momentum is. It's basically going to tell us, like for instance, if we were moving this direction and we compute our error again at this point, that second term is basically going to inform the model that we were moving in this direction already at some speed. And so when we compute the weight, because of the directionality, by summing this momentum term onto our error, it's just going to sum this sort of movement onto how we change our weights at this point, right? So if we're moving here, then when we compute the weights at the next segment, at the next point we decide to do it, momentum is going to keep us moving this way, right? Because we were already traveling this way to begin with. Now I'm going to plug in my laptop. This chart. I asked her to bring this. I'm not just taking this, FYI. Hope you all know. But yeah, that's basically how momentum is going to apply here. And oh no, there's only a single USB-C port on my computer. That's okay though. Okay, maybe not, but yeah. So, does anybody have any questions in like so far with just that really physical and that like other mathematical representation of momentum? Does it all seem pretty good? I think this is going to come back to life. Maybe I'm going to steal that from you. Thanks.
Steps.
What's up? But yeah, I mean, once again, if we just like recall that equation that's totally not on the screen anymore, the concept of momentum is a fairly simple one, right? It's just basically summing the movement from our past iteration onto our current iteration. And we can look at this sort of more physically again. So let's say we're moving down some air. I really like this shape, I guess, but let's say we're moving down this 2D air landscape. And previously, we computed our error here, and we got this derivative. And now we compute our error here, and we get this derivative. Well, even though we're at a local minima here and we might think we're happy, because we're summing this term on here onto our change in weights, it's gonna basically mess with how this term is gonna be represented. And there's gonna be this other momentum scaling factor that's similar to the learning rate that basically changes how much momentum is applied. And you can sort of see that in that, like if this gamma value is, I hope it's a gamma. If that gamma value is really high, then your momentum is going to increase, right? The weight that your previous trial had on this trial is going to go up, right? Because it's just basically scaling momentum up. So let's say we have a little bit of momentum here. This arrow, although it's going to be flat when we just look at that iteration alone, since we're using momentum, we take this downward steep go and moving curve into consideration as well. So actually, our error is going to look sort of like this, right? And that's going to basically help us keep going because we've sort of moved how it's looked. Sorry, it's not going to look like that. It's going to look like this. Oops. But yeah, that's just going to help us. But yeah, I mean, basically, that's all momentum is. It's just sort of factoring in how we're moving. If we're moving in a certain direction, we just don't want to stop. And that will just help us get out of the local minima that end up showing up. Any questions on momentum? So we're going to cap this discussion off with just some gnarly error plots. So what are some problems with these? What can we think of that might be tough for something like this weird saddle looking thing? Any thoughts? Just visually, like, okay, let's just not even think about error. What if we're just a ball and we're trying to roll onto like a local minima? How might this be troublesome? Yeah, go for it. Yeah, so like as a ball, if we're just trying to roll into like some saddle point, some local minimum, it's really easy to just kind of get like, if we're trying, we want to roll along this sort of line here where you see that kind of flatness. But if we roll a little bit like too far, we're just going to roll off the edge and kind of fall to our deaths. So this is another sort of optimization problem called finding the saddle point, which is basically the like little flat bit amongst like a bunch of kind of different oscillatory kind of weird geometric shapes. And these saddle points may even find their way into more complex looking curves. Like here, for instance, you see there's like a little saddle point here, but you also have two other minima here. And then you also, like, as you kind of scale up, you just encounter more and more weird shapes that will really mess you up in like how you calculate things. And yeah, this is a really excellent article that talks about this optimization problem of finding saddle points in a local minimum. So if you get a chance, you give that a read. But yeah, I mean, this is just something to look at and consider. Like this problem, even though it's just as simple as saying, hey, I want to find some local minima or some saddle point. It can get really convoluted and really complex really quickly. And there are just millions, okay, maybe not millions, but there's a lot of pitfalls to this simple optimization task. And I also want to emphasize that this process of gradient descent is sort of the kind of backbone of building neural networks and building up machine learning models, because at the end of the day, like we're trying to fit a function to some set of data. And to know how well we're doing, we need to know how the error is looking. But the best possible thing that we can fit is the thing with the lowest error. So we have to iteratively search for that. And in essence, like iterating through gradient descent and comparing these gradients and seeing how they look is very much the core of how a model is learning. It's just looking at the errors and trying to figure out a way to make them small and tune its parameters until they get small. A good physical picture for this maybe is you can kind of think of it as like this model is trying to come to this optimal point where it's really happy. And if it kind of moves onto a point of error that goes up, you kind of like smack it and you say, well, that's not so good. And then it's going to change its behavior. It's going to mutate its values. So that moves to a different point of error. And if the error looks better, you're just going to maybe give it a treat. You're going to say, good job. And the model is going to try its best to look around and find where the function it fits, the parameters it chooses to fit the function with, give an output with the lowest error. But yeah, that's basically gradient descent. And we covered this from a pretty high level mathematical view, not high level, from a just a pretty high level. And maybe later on, we'll talk about how exactly the math works, but I guess that depends on interests. But yeah, that's pretty much all we have for today. Any additional questions on this sort of thing? All right, well, we can just wrap it up then. Thanks for coming. Oh yeah, what's up?
So those error profiles, they come from when you try to approximate your function to the data points that you have.
Yeah.
What kind of function we usually approximate to the data points? Is it usually like a linear or?
Yeah. So there's a lot of different things that we can approximate. So we can have like I demonstrated the linear regression task, but there's also the thing called logistic regression, for instance, where we fit like a logarithmic function and try to split points across another. There's another thing called something like a support vector machine, which basically draws hyperplanes to separate points. So let's say we got this set of points here. And we had this set of points maybe here. What something like, oh, and these are two distinct classes that maybe we want to classify. So maybe like the blue is like rocks and the orange is sticks, and we're building a neural network to classify rocks and sticks. And we're using an SVM, a support vector machine. What the support vector machine is going to do is it's going to try to figure out a way to draw like a line or something that splits these two up. And how we would measure error in that case is we just see like how many points fall into the wrong categories, for instance. And like oftentimes as we get into more complex networks and complex data, like we might even fit various nonlinear functions that are like maybe cubic, like something like this, you know, and we can even kind of like try different functions. So we might try this cubic function and we see that error is high. Maybe we'll try this like, is that still cubic?
Yeah.
Okay, is this quadratic now or quintic? Quartic? Sure, yeah, we'll try a different polynomial magnitude. Like there's a lot of variance in how we can generate models and functions of best fit that we're gonna change based off what we basically tell our computer, right? Because for different tasks, there's gonna be different models that are advantageous. Like, for instance, if we had a simple linear regression that we're trying to fit, like doing some wonky, like eighth dimensional polynomial function is going to be a terrible way to do it, because what is that going to do, right? It's going to see this at a go away. It's going to see this simple set of data points and it's going to draw like a curve like this, right? Because it has that many degrees of freedom and it can do that. And by doing that, it might actually fit a lot more of the data points than something like this, right? It might actually get a lower error than that. But that's going to be a problem called overfitting. We're going to talk more about it. Yeah, any other questions? All right, well, I can call it a day then.